The universe is not showing us its true size. It gives us a night sky full of familiar stars, then hides almost everything that matters behind distance. Darkness, invisible matter, and horizons no light can cross. Earth is not simply small, it is tucked inside a galaxy, inside a filament, inside a cosmic web, inside a visible bubble that may be only a keyhole into something far larger. In this journey from the moon to the edge of sight, Slow Space Stories follows the scale that quietly breaks human intuition. If this kind of calm cosmic storytelling helps you relax, please give the video a like. Subscribe for more slow science journeys, and share it with someone who loves space before sleep. Thank you for spending your time here. What time is it where you are watching? And from which part of the world? Leave a comment so this quiet community can travel together. Now, let us step into the true scale of the universe. The sky does not lie exactly. It withholds proportion. On a dark night, far from city light, human sight can gather a few thousand stars from the blackness overhead, enough to make the heavens feel crowded and almost complete. The impression is powerful because the eye has no natural ruler for distance. A bright star nearby and a bright star far away both arrive as points of light. A neighboring planet can look more commanding than a giant star many hundreds of light years beyond it. The visible sky feels like a map, yet it is mostly an illusion of nearness. Almost everything seen without a telescope belongs to a thin, local sample of the Milky Way, a shallow glance through one small region of one galaxy. The whole galaxy stretches about 100,000 light-years across, but ordinary vision reaches only a modest portion of that breadth. It is less like seeing an empire from above and more like seeing a few lamps along one road, then mistaking those lamps for the shape of all civilization. This is the first distortion in the mind-bending scale of the universe. The cosmos does not appear small because it is small. It appears manageable because most of it is hidden by distance, darkness, time, and the limits of the senses. The moon looks close because it has shape. Mars looks like a reddish point because it is too far for the eye to resolve. The Andromeda Galaxy can appear as a faint smudge in unusually dark skies, but its softness gives little hint that it contains roughly 1 trillion stars and lies millions of light years away. The sky compresses everything. It lays nearby worlds, distant suns, star clouds, and entire galaxies onto the same dark surface, as though all of them belonged to one ceiling. The mind receives that flattened image and makes a quiet mistake. It treats the universe as something overhead, when the real universe surrounds Earth in every direction, deeper than sight can follow, and older than any familiar measure can hold. For most of human history, the error was unavoidable. The naked eye gave no reliable way to separate a star from a planet, or a nebula inside the Milky Way from a galaxy far beyond it. When the distance to Andromeda was measured with pulsating stars, the scale of existence changed without the sky visibly changing at all. The same smudge had always been there. What changed was the meaning of its faintness. It was not nearby haze. It was another galaxy, set so far away that its light crossed intergalactic space before reaching Earth. In that single correction, the Milky Way stopped being the universe and became one object inside it. The visible heavens did not grow brighter. They grew deeper. Scale in astronomy often changes this way, not by adding a new object to the sky, but by discovering that an old object has been misunderstood. A point becomes a star. A star becomes part of a galaxy. A nebula becomes another galaxy. A galaxy becomes one member of a cluster. A cluster becomes a knot in a filament. A filament becomes one strand in the cosmic web. At every step, The previous picture was not entirely false, only too narrow. The ordinary night sky is therefore not a doorway into the whole cosmos. It is a keyhole. Through it appears a tiny local arrangement of light, while most of the structure remains outside the frame. Beyond the familiar stars lies the rest of the Milky Way. Beyond the Milky Way lies the local group, where galaxies hold one another in a slow gravitational association. Beyond that lie clusters and superclusters, not arranged randomly, but drawn into threads, walls, and knots around enormous regions of near emptiness. The large-scale universe has architecture. It has a pattern made not only by what shines, but also by where almost nothing shines at all. That pattern is difficult to sense from Earth because the planet is embedded within it. A creature inside a cathedral cannot understand the whole building by staring at one stone. A civilization inside a galaxy cannot understand the cosmic web by looking only at nearby stars. The difficulty is not only observational, it is psychological. Human scale is built from things that can be crossed, touched, or returned from. A mountain can be climbed. An ocean can be crossed. Even the far side of Earth is still part of a closed surface where distance remains connected to memory and motion. Cosmic scale breaks those habits. Light itself, the fastest messenger allowed by nature, becomes slow against the size of the universe. The sun is only minutes away in light travel time. The nearest stars are years away. The center of the Milky Way is tens of thousands of years away. Nearby galaxies are millions of years away. The most distant observable light began its journey before Earth existed in its present form, before the sun had planets, before the atoms in living bodies had gathered into anything alive. To look outward is not simply to look across space. It is to look backward through time, because the universe does not reveal itself as it is now. It reveals itself as light had time to arrive. This time depth makes the scale stranger still. The edge of the observable universe is not a wall where space ends. It is the limit of what light has been able to bring since the hot early universe became transparent. The observable region is vast, roughly 93 billion light-years across. Not because light has traveled that distance in a straight, static arena, but because space itself has expanded during the journey. A galaxy whose light has traveled for more than 13 billion years is now much farther away than that light travel time might suggest. The distance has stretched beneath the moving photon. The universe is not merely large. It is enlarging. The map is changing while the message crosses it. That fact turns ordinary intuition inside out. A distant galaxy can be visible as it was long ago, while its present location may already be beyond any possible future contact. Some light now being emitted in remote regions will never reach Earth, no matter how long the future lasts, because the space between those regions and the Milky Way expands faster than the light can close the gap. The visible universe is therefore not the same thing as the reachable universe. Sight extends farther than influence. Knowledge reaches places that no signal can ever answer from again. Even this enormous visible realm may be a small part of a much larger whole. The word observable carries the crucial warning. It does not mean total. It means limited by time, light, and expansion. Beyond the cosmic horizon, there may be more galaxies, more web, more voids, more regions of space arranged under the same laws, or perhaps under conditions that remain forever inaccessible. The known universe is centered on Earth only in the sense that every observer stands at the center of their own horizon. There is no evidence that Earth occupies a privileged middle of all space. The spherical view is a consequence of observation, not importance. It is a bubble of visibility drawn around one planet by the age of the cosmos and the speed of light. The deeper problem is that the visible universe is not only large and limited, it is also poorly understood. The matter that shines, the atoms in stars, planets, gas, oceans, stones, and bodies, accounts for only a small portion of the cosmic inventory. Most matter appears to be dark, known through gravity rather than through light. Most of the total energy content appears stranger still, tied to the accelerating expansion of space. The galaxies that make the sky magnificent are only the luminous part of a structure dominated by things not directly seen. In that sense, scale is not the only shock. Visibility itself is misleading. The cosmos is not mostly stars. It is not mostly galaxies. It is mostly darkness, distance, invisible mass, and expanding space. The universe is measurable enough to be studied, but not simple enough to be settled. Its largest questions keep returning with deeper complications. The first lesson, then, is not simply that the universe is big. That word is too small for the task. The lesson is that every familiar sense of proportion fails before the real structure appears. The night sky offers beauty, but not scale. The stars offer orientation, but not context. The visible cosmos offers a horizon, but not an edge. From Earth, the universe looks like a dark bowl scattered with points of light. In reality, Earth sits inside a galaxy, inside a group, inside a supercluster, inside a filament, inside a web, inside a horizon that may be only the small, illuminated opening of something far larger. The keyhole is bright enough to invite measurement, but narrow enough to mislead. Before the outer architecture can be followed, the first distances must be crossed close to home, where even the Moon, Mars, and the farthest human spacecraft begin to show how quickly ordinary scale falls away. The Moon is often treated as Earth's companion because it returns so faithfully to the sky, changing shape with the month, lifting tides, and holding a familiar place in human memory. Its nearness is real, but only by astronomical standards. The average distance from Earth to the Moon is about 384,400 kilometers, far enough that Earth could fit about 30 times across the gap. A beam of light crosses that distance in a little more than 1 second, but a spacecraft still needs days to travel it, and every journey there has required an act of immense engineering focus. The first step away from Earth is not gentle. It is a climb out of a gravity well, a passage through radiation, vacuum, orbital mechanics, and a silence where ordinary motion begins to lose meaning. The Moon looks close because it is large enough to show a face. In reality, it is already remote enough to turn Earth into an object, a bright globe hanging over a gray horizon, no longer the surrounding world, but a thing in space. That shift matters because it is the first correction to human scale. The nearest world is not near in any lived sense. It is merely the closest place where distance has not yet become overwhelming. Mars expands the lesson. At its closest approaches, Mars lies tens of millions of kilometers from Earth. At its farthest, when the two planets sit on opposite sides of the Sun, the distance stretches to hundreds of millions of kilometers. The planets are neighbors only because the rest of space is so much larger. A signal traveling at light speed may take minutes to cross the gap one way, and that delay is enough to change the meaning of presence. A rover on Mars cannot be driven like a vehicle on Earth. Commands must be prepared, transmitted, received, executed, and answered across a pause built into the structure of the solar system. There is no immediate correction, no ordinary conversation, no shared moment in the human sense. Mars is close enough to photograph Earth as a pale point in its sky, but far enough to make every exchange with Earth feel like communication with the past. From the Martian surface, the home planet no longer has continents or weather systems visible to the naked eye. It becomes a small blue-white mark among other lights. All the noise of biology, history, cities, languages, and memory is compressed into a dot. The reduction is not emotional exaggeration. It is geometry. Distance removes detail until the world that contains everything familiar becomes one more point of reflected sunlight. Moving outward from Mars, the solar system becomes less like a set of planets and more like a vast arrangement of intervals. The asteroid belt lies between the orbits of Mars and Jupiter, but even there, the popular image of crowded rocks is misleading. The belt contains many objects, yet the spaces between them are immense. A spacecraft can pass through it without weaving through a field of stones. Farther out, Jupiter dominates by mass, a planet so large that its gravity shapes the architecture around it. Saturn follows with its rings and many moons. Then Uranus and Neptune, cold giants, moving slowly through the dimmer reach of sunlight. Each orbit widens the spacing. The sun still rules, but its heat thins. Its light weakens by the square of distance, and the worlds become colder, slower, and more isolated. Neptune, the outermost major planet, is so far from the sun that one orbit takes more than a human lifetime. Yet Neptune is not the edge. Beyond it lies the Kuiper Belt, a region of icy bodies where Pluto moves, along with many other small worlds left from the formation of the solar system. These objects are not debris in a careless sense. They are preserved fragments of an earlier planetary order, cold records from the outer disk where the sun's warmth was never strong enough to erase them. Even there, the solar system is not finished. Beyond the Kuiper Belt, in a much more distant and uncertain realm, astronomers infer the existence of the Oort cloud, a vast reservoir of icy bodies extending far into the sun's gravitational influence. It has never been directly imaged as a whole, yet long-period comets suggest its presence. If the Kuiper Belt is a scattered shore, the Oort cloud is a faint outer mist, so broad that passing through it would require timescales longer than recorded civilization. This is where the meaning of leaving the solar system becomes complicated. A spacecraft can cross the heliopause, the boundary where the solar wind gives way to interstellar space, and still remain deep inside the sun's wider gravitational domain. The farthest human-made objects, the Voyager spacecraft, have entered interstellar space in that narrower plasma sense, but they have not escaped the full architecture of the solar system. Voyager 1, launched in the late 1970s, is now beyond the planets, beyond the direct breath of the solar wind, carrying instruments that were built in another technological era and a golden record intended as a greeting to any intelligence that might someday encounter it. Its journey is extraordinary, but the scale around it makes the achievement quiet and almost lonely. After decades of travel, it remains only a short way outward compared with the full distance to even the inner Oort cloud. To reach that region may take centuries. To pass through the outer cloud may take tens of thousands of years. The probe moves faster than any ordinary human vehicle. Yet against interstellar distances, it drifts like dust. The nearest known star system, Alpha Centauri, lies a little more than 4 light-years away, with Proxima Centauri as the closest star to the Sun. That distance is small on a galactic map and almost impossible on a human one. Light itself needs more than 4 years to cross it. A spacecraft moving at Voyager's speed would need many tens of thousands of years. The interval between neighboring stars is therefore not empty in the casual sense. It is emptiness with duration. It is distance so wide that even fast machines become archaeological objects before they make meaningful progress. A message sent today toward Proxima Centauri would not arrive until years from now, and any reply would require the same delay in reverse. The nearest star is close enough to be part of the Sun's neighborhood and far enough to dissolve ordinary communication. This is the second correction to scale. The solar system seems large until the distance between stars appears. Then the solar system becomes a small local clearing around one lamp, and the stars become other lamps separated by a darkness too wide for quick crossing. Humanity's own radio presence shows the same limitation from another angle. Since the rise of powerful radio transmissions, electromagnetic signals from Earth have spread outward at light speed, forming an expanding bubble of human-made noise around the planet. By cosmic standards, that bubble is tiny. It reaches only a limited neighborhood of nearby stars, a barely noticeable sphere inside the Milky Way. Beyond it, nothing produced by human technology has arrived. No television signal, no radar pulse, no accidental leakage, no deliberate greeting. The overwhelming majority of the galaxy has received no sign that Earth hosts a technological species. Even within the bubble, signals weaken as they spread. They dilute across the surface of a growing sphere, sinking into background noise, becoming harder to separate from the natural radio murmur of stars, gas, and cosmic processes. The idea that humanity has loudly announced itself to the galaxy is more fragile than it seems. The announcement has barely begun, and it may already be faint. This changes the feeling of the question of contact. Silence does not necessarily mean absence. It may mean that the distances are too large, the signals too weak, the timing too narrow, and the windows of detection too brief. A civilization could exist beyond the human radio sphere and remain completely unaware of Earth, not because it is hidden by intention, but because the evidence has not yet crossed the dark. In this way, even the local universe begins to reveal its architecture of separation. The Moon teaches that the nearest body is distant. Mars teaches that neighboring worlds cannot share immediacy. The outer planets teach that sunlight itself becomes a dwindling thread. The Oort cloud teaches that the Sun's realm is larger than the planetary map suggests. The nearest stars teach that interstellar travel belongs to timescales beyond civilization as usually imagined. The radio bubble teaches that even light-speed communication may occupy only the smallest fraction of the galaxy's depth, close to home, before the Milky Way is considered as a whole. Space has already become a structure that isolates as much as it connects. The first outward journey does not yet reach the cosmic web, the voids, or the edge of sight. It simply moves from Earth to the nearest margins and finds that ordinary proportion has already failed. The solar system is not a compact neighborhood suspended under the stars. It is a wide, cold gravitational territory around one ordinary star, bordered by ancient ice and opening into a darkness where the nearest suns are separated by years of light. From that perspective, the next scale is not a simple enlargement. It is a change in category, because the Sun and all its planets are only one small system inside a galaxy whose full size remained hidden from human understanding until very recently. The Milky Way first appears as a pale band because Earth is not looking at the galaxy from outside. It is looking from within the disk, through crowded fields of stars, gas, dust, and dark clouds that soften the light into a long milky river across the night. That band is not a separate object hanging beyond the stars. It is the galaxy itself, seen edgewise from one of its inner spiral features, the Orion Arm, where the Sun moves with planets, ice, dust, comets, and all the quiet machinery of the solar system. The view is intimate and misleading. A person beneath a dark sky is not looking at the Milky Way in the way a telescope image shows Andromeda. There is no grand spiral laid out in front of the eye. There is only a crowded interior view, a line of sight through the stellar city from one unremarkable street. The sun is one star among hundreds of billions. It is neither near the center nor near the edge, but located in a modest region of the galactic disk, far from the central bar and far from the outermost thinning halo. Around the galactic center, the sun travels in a long orbit that takes hundreds of millions of years to complete. Since Earth formed, the solar system has circled the Milky Way many times, passing through, changing neighborhoods of gas clouds, stellar association, and spiral structure. The galaxy, which can seem fixed in the sky, is instead a rotating system of immense mass and slow motion. Stars do not sit in a painted pattern. They stream, gas clouds collapse, new stars form in dusty nurseries, old stars drift into quieter orbits. Supernovae seed the surrounding medium with heavy elements. The disk breathes across deep time, not as an organism, but as a gravitational system where matter keeps being rearranged under forces that act too slowly for a human life to perceive. At the center lies Sagittarius A star, the compact radio source that marks the Milky Way's central supermassive black hole. Its mass is millions of times the mass of the Sun, yet it occupies a region far smaller than the galactic bulge around it. Near that center, stars whip around on tight, rapid paths, revealing by their motion the dark object they orbit. The black hole is not a cosmic drain swallowing the galaxy. It is a central mass embedded within a much larger structure. Important, extreme, but not the only fact of the Milky Way. Around it spreads the bulge, the bar, the disk, the spiral arms, and the halo of old stars and globular clusters. Beyond the visible disk lies something larger still, the galaxy's dark matter halo, an invisible mass distribution inferred from the way stars move and from the way galaxies hold together. The luminous Milky Way is therefore only part of the Milky Way. The stars make its shape visible, but gravity suggests a larger body that cannot be seen directly. This was not always understood. Even the idea that the Milky Way is a galaxy among others is recent by the standards of human thought. For centuries, the pale band overhead was a mystery of light. Telescopes resolved parts of it into countless stars. But the broader question remained unsettled. Were the faint spiral nebulae seen through observatories small structures inside the Milky Way? Or were they separate star systems far beyond it? The answer mattered because it decided whether the Milky Way was the whole universe or only one member of something much larger. In 1920, astronomers debated the issue publicly, with one side defending a vast Milky Way that contained the visible cosmos and the other arguing for island universes beyond it. The sky had not yet surrendered its distance. The decisive change came when variable stars were identified in Andromeda, stars whose rhythms allowed their true brightness and distance to be estimated. Once Andromeda proved too distant to belong to the Milky Way, the mental boundary of the universe broke open. A faint patch in the sky became another galaxy, and the Milky Way became one island among many. The scale did not expand because matter moved outward. It expanded because understanding finally caught up with distance. Andromeda lies about 2.5 million light-years away, close enough to be part of the local group, yet far enough that its light began its journey before the rise of modern humans. It contains hundreds of billions of stars, perhaps more than the Milky Way, and is moving slowly toward this galaxy under mutual gravity. In the far future, the two great spirals will merge, not by stars crashing together in large numbers, because the spaces between stars are too wide, but by gravitational fields reshaping their orbits over immense time. This future merger shows that galaxies are not isolated ornaments. They interact. Approach. Strip gas from one another, swallow smaller companions, and rebuild their forms. The Milky Way itself carries signs of past meals. Streams of stars loop through its halo. Remnants of dwarf galaxies torn apart by tidal forces. The disk may look orderly from a distance, but its history is layered with accretion, disturbance, and slow assimilation. The galaxy is a home, but it is also a record of collisions. Around the Milky Way move smaller companions, including the Magellanic Clouds, irregular galaxies visible from the southern hemisphere, whose gas and stars are being shaped by their encounter with the larger spiral. Other dwarf galaxies orbit more quietly, some faint enough that only careful surveys reveal them, together with Andromeda, Triangulum, and many smaller systems. The Milky Way belongs to the local group, a gravitational family spread over millions of light years. The name sounds modest, and in cosmic terms it is. Yet within it are scores of galaxies, dark matter halos interlaced with visible matter, and a future already partly written by gravity. The local group is bound. It can resist the general expansion of the universe because its members are close enough and massive enough to hold together. But beyond that local binding, the larger cosmos begins to stretch away. This is where the galaxy becomes both enormous and small. The Milky Way is vast compared with the solar system, but on a map of nearby galaxies, it is one spiral among a small collection. On a map of clusters and superclusters, it becomes a dot. On a map of the cosmic web, even the local group becomes a minor brightening along a filament. The radio bubble around Earth makes the contrast sharper. Humanity's electromagnetic trace extends only a thin distance into the surrounding disk, a small sphere inside one galactic neighborhood. Even if every signal remained clear, which it does not, the overwhelming majority of the Milky Way would still have no evidence of Earth. The galaxy that feels like home from within has scarcely been touched by human presence. Not by spacecraft, not by signals, not by memory. The Sun's neighborhood is only a local patch of a vast stellar system, and that system is only one of an enormous number of galaxies spread through observable space. Estimates of the number of galaxies have changed as telescopes improved, because many galaxies are faint, distant, small, or hidden in earlier surveys. What matters here is not one exact count, but the scale implied by it. The universe contains not merely many stars, but many galactic systems, each with its own history of gas, dust, dark matter, star formation, black holes, mergers, and loss. The Milky Way is not diminished by this. It becomes more interesting because it is no longer the whole stage. It is one example of a kind of structure repeated across space in variations too numerous to hold in ordinary thought. Spiral galaxies, elliptical galaxies, irregular galaxies, dwarf galaxies, ancienne galaxies, starburst galaxies, galaxies with quiet centers, and galaxies with active black holes. All occupy the deep field of the cosmos. The night sky hides this abundance because most galaxies are too faint for unaided sight. And because the Milky Way's own dust blocks parts of the view, the platform of observation is also an obstruction. To map the universe, astronomers must look through the galaxy that contains them, correct for its dust, peer around its crowded plane, and translate faint light into distance. The result is a humbling reversal. The Milky Way once seemed like the full container of existence. Now it is a location problem, a luminous foreground that must be understood before the deeper background can be read. From this galactic neighborhood, the next scale appears slowly. Galaxies are not sprinkled evenly through the dark. They gather into groups, chain, and clusters, while between those concentrations open vast spaces with very few galaxies at all. The discovery that the Milky Way is one galaxy among many did not merely add more islands to the map. It revealed that the ocean itself has structure. Some regions are crowded with matter. Others are almost empty. The next step outward is therefore not simply toward more galaxies, but toward the great absences between them, the voids where the lights thin so severely that the universe begins to look less like a field of stars and more like a pattern drawn around nothing. The Boötes Void was not found as an object, but as an absence. Astronomers mapping galaxy redshifts in the late 20th century were not searching for a cosmic desert. They were trying to place galaxies in 3 dimensions, turning points of light into a deeper map by measuring how fast their light had been stretched by the expansion of space. When the positions were plotted, a strange gap appeared near the constellation Boötes, a roundish region where the expected galaxies were mostly missing. The first impression was not discovery in the usual sense. It was suspicion. Empty regions can be produced by incomplete surveys, poor sensitivity, dust, selection effects, or the simple fact that very faint galaxies are easy to overlook. The data had to be checked, extended, and compared. Yet the gap remained. It was not a hole in space, not a physical boundary or a wound in the fabric of the universe, but a vast region with far fewer galaxies than ordinary cosmic averages would suggest. Its diameter is roughly 330 million light-years, a scale so large that thousands of Milky Way-sized galaxies could be lined across it. In a volume that might have been expected to contain thousands of galaxies, only a small number have been identified, many arranged along a thin internal structure rather than spread evenly through the whole space. The meaning of such a void is difficult to picture because emptiness does not give the mind many handles. A galaxy can be imagined through stars, arms, dust lanes, and bright centers. A cluster can be imagined as a crowded city of galaxies. A void is defined by the lack of such things. It is a region where the cosmic map grows quiet, where the lights thin until the surrounding web becomes more important than the interior. If a galaxy like the Milky Way were placed near the center of such a void, the history of astronomy might have unfolded differently. The sky would still contain local stars, planets, and the pale band of its own galaxy. But the deeper telescopic background would be poorer. Faint external galaxies would be fewer, farther, and harder to interpret. The realization that other galaxies exist might have arrived later, not because the universe was different, but because the evidence available from that address would have been sparse. A void therefore reveals something unsettling about observation itself. Cosmology is not performed from nowhere. It is performed from a location, and location decides which clues are easy to see. The Boötes Void is large, but it is not unique. Voids are not rare accidents scattered through an otherwise crowded universe. They are one of the dominant forms of cosmic structure. On the largest scales, galaxies gather into filaments, sheets, clusters, and knots, while the spaces between them open into immense underdense regions, taken together. These voids occupy most of the volume of the observable universe. The exact fraction depends on how voids are defined, but the broad lesson is stable. Matter is not spread evenly. Light is not spread evenly. The cosmos resembles a vast foam, with galaxies and gas clinging to the walls between bubbles of relative emptiness. In that image, the voids are not interruptions in the pattern. They are the pattern's largest features. The luminous structures that attract the eye are the boundaries. The dark interiors take up the room. This reverses the ordinary feeling of the night sky. The human eye notices stars and assumes the universe is chiefly made of bright things separated by darkness. At cosmic scale, the darkness is not merely background. It is the main volume, and the bright things are delicate traces along its edges. The origin of this foam-like arrangement reaches back to the early universe. The hot young cosmos was extremely smooth, but not perfectly smooth. Tiny density variations were present, small enough to look almost insignificant, yet real enough for gravity to work on them. Regions with slightly more matter pulled in additional matter. Regions with slightly less matter gave it up to their denser surroundings. The differences grew slowly at first, then more decisively, over hundreds of millions and then billions of years. Gravity amplified those early irregularities. Dense regions became the seeds of galaxies and clusters. Underdense regions expanded more freely and became emptier. The voids are not places where matter was removed from a finished universe. They are regions where matter never gathered as strongly, where the early statistical texture of the cosmos matured into architecture. That distinction matters because it makes emptiness part of cosmic history, not the absence of history. A void is not nothing in the absolute sense. It can contain thin gas, dim galaxies, dark matter, radiation, and the continuing expansion of space. But compared with the filaments and clusters around it, it is poor in luminous matter. Its emptiness is relative and still immense. The average distance between galaxies inside a large void can be far greater than in more crowded regions. Gravity there is weaker in its local grip, and matter has tended to stream outward toward the denser walls. The void becomes emptier as the surrounding structures become richer. The result is a universe in which absence has shape, and that shape helps define where galaxies can grow. Earth's own wider environment may be tied to this same principle. The Milky Way appears to lie within a comparatively underdense region, sometimes described as the local hole or the KBC void, a broad zone containing fewer galaxies than surrounding space. Its exact scale, depth, and cosmological importance remain debated, but the possibility is significant. If the local universe is less dense than average, then measurements made from this region may carry the imprint of that environment. Galaxies in and around an underdense region do not simply sit in place. Denser regions beyond the void exert gravitational influence, and matter tends to flow toward them. Space within an underdense region can appear to expand differently from the cosmic average. Some researchers have explored whether this could contribute to the mismatch in measurements of the universe's expansion rate. It may not solve the problem. It may be only a piece of a larger tension. Yet it shows how a question that sounds universal can be entangled with geography. The expansion of the universe is a cosmic property, but the measurement is made from a particular cosmic address. If that address lies in a quieter than average region, the view may be subtly biased. The thought is humbling because it makes the observer part of the problem. For centuries, the Copernican lesson has been that Earth is not central, not privileged, not a special seat from which the universe arranges itself. Modern cosmology extends that humility by assuming that, on sufficiently large scales, the universe is broadly the same everywhere. Voids complicate that feeling without necessarily overthrowing it. They show that sameness appears only after enormous averaging. Locally, the cosmos can be strongly uneven. One region can be crowded with clusters, another stretched into relative emptiness. A civilization born inside a rich cluster would inherit a different sky from one born in a deep void. Its telescopes would face different foregrounds, different nearby galaxies, different gravitational flows, and perhaps different temptations when building a theory of the whole. The universe may be statistically uniform at the largest scales, yet still locally capable of misleading any observer who mistakes a neighborhood for the whole. This is the deeper importance of the great voids. They are not just giant empty rooms between more interesting structures. They are reminders that the visible universe is shaped by contrast. Filaments matter partly because voids surround them. Clusters stand out because emptier regions frame them. The cosmic web is not a web made only of strands. It is a web made of strands and gaps together, with each giving meaning to the other. Without voids, the universe would be a smoother fog of matter, less structured, less legible, and perhaps less capable of producing the kind of concentrated environments where galaxies assemble efficiently. Emptiness, in this sense, is not passive. It is a sculpting condition. It channels matter away from broad regions and toward narrow walls. It helps stretch the universe into a network. It makes the places of formation rarer and more defined. At the edge of a void, gravity gathers what the void does not keep. Along the walls, gas and dark matter collect. At intersections, clusters grow. The great absence becomes the reason the luminous pattern has such sharpness. Seen from within a galaxy, space feels like distance between stars, seen from the scale of hundreds of millions of light years. Space becomes a distribution of presence and absence, with absence taking the greater share. The Boötes Void gives that idea a name and a scale, but it is only one chamber in a much larger foam. The Milky Way, the local group, and all nearby galaxies exist not in a simple field, but on the structured margins of emptiness. The next movement outward has to follow those margins, because the matter that did gather did not arrange itself randomly. It formed corridors, sheets, and bridges across the dark, a connected architecture where galaxies become bright knots along invisible lines. The voids reveal where the universe is missing matter. The cosmic web reveals where that missing matter went. The cosmic web begins where the voids end, along the thin walls and stretched corridors where matter refused to disappear into emptiness. It is not visible to the naked eye, and even through powerful telescopes, it does not appear as one shining structure. Its presence is assembled from many kinds of evidence galaxy positions, redshifts, gravitational lensing, hot gas, faint hydrogen emission, and computer simulations that begin with the early universe and allow gravity to work across billions of years. What emerges is not a random universe. Galaxies do not fill space like dust stirred evenly through a room. They gather along filaments, flatten into sheets, cluster at intersections, and leave enormous voids between them. The largest recognizable pattern in the cosmos is therefore not a wall, a galaxy, or a cluster, but a network. Its strands can extend for hundreds of millions of light years. Its nodes can contain thousands of galaxies. Its empty chambers can be wider than any ordinary map of the night sky could suggest. The cosmic web is the structure that makes the universe look, at its greatest scale, like foam threaded with light. Yet most of the web is not made of bright galaxies. The galaxies only mark the densest places, like dew beads on a nearly invisible thread. The deeper structure is gas and dark matter, spread thinly across immense distances, shaping where ordinary matter can collect. In the early universe, dark matter had a decisive advantage. It did not interact with light in the same way ordinary matter did, so it could begin clumping under gravity while hot ordinary matter remained coupled to radiation. As the universe expanded and cooled, normal gas fell into the gravitational wells already shaped by dark matter. Those wells became the scaffolding of later structure. Gas collected there, cooled where conditions allowed, formed stars, and eventually built galaxies. The visible web came after the invisible one. This order matters because it means the universe was not assembled from bright objects outward. The bright objects formed inside a darker architecture already prepared for them. Galaxies are not simply islands in empty space. They are growths along an unseen framework. For a long time, that framework could be inferred more easily than directly seen. Galaxy surveys revealed the pattern clearly enough. When astronomers measured the distances to large numbers of galaxies, the dots began to arrange themselves into chains and walls. Voids appeared between them. Clusters formed at their crossings. Simulations based on gravity and dark matter produced similar networks, suggesting that the pattern was not an observational accident. But the filaments themselves remain difficult to observe. The gas between galaxies is extremely faint. It is diffuse, spread so thinly that ordinary intuition about clouds or streams fails. A filament may contain enormous total mass and still glow with a softness almost beyond detection. Capturing it requires long exposures, sensitive instruments, and a careful separation of true signal from background noise. This is why direct images of the web are so important. They turn a structure known through maps and models into something more concrete. A physical bridge of matter stretching between galaxies. When faint hydrogen light from a filament is detected, it reveals not just a location but a process. Gas is not merely sitting there. It is part of the supply system of galaxies. It flows along the filaments toward denser regions, feeding star formation and helping galaxies grow. The web is therefore not only architecture, it is movement. At the intersections where filaments meet, matter accumulates into galaxy clusters, the largest gravitationally bound systems in the universe. These clusters are not merely collections of galaxies. They are immense reservoirs of hot gas and dark matter, with galaxies moving through them like bright particles inside a much larger gravitational field. Between the clusters, the filaments carry matter across the dark, linking regions that would otherwise seem separate. On smaller scales, gravity binds moons to planets, planets to stars, and stars to galaxies. On the largest scales where gravity can still shape matter before expansion stretches it too far, the web is the result. It is the memory of tiny early fluctuations amplified into cosmic geography. A slight excess of density in the young universe becomes, after enough time, a filament. A slight deficit becomes a void. The beauty of the web is that it links the smallest early irregularities to the greatest present structures. It is quantum texture made astronomical by gravity. This does not mean every detail is settled. The web is known, but not simple. Gas in filaments can be cold, warm, hot, ionized, shocked, or hidden at wavelengths that are difficult to measure. Some of the ordinary matter expected from calculations appears to reside in this faint intergalactic medium, making the web important for solving the problem of missing baryons, the ordinary protons and neutrons that should exist but are hard to locate in the nearby universe. The matter is not missing in the sense of being absent from reality. It is missing from easy observation. It may be spread thinly through the spaces between galaxies, too diffuse to shine brightly, yet still enough to complete the cosmic accounting. In this way, the web carries both structure and concealment. It shows where matter gathers, and it hides much of what it contains by stretching it across distances too broad for ordinary brightness. The web also changes how galaxies are understood. A galaxy is not an isolated system that forms once and then evolves alone. It lives inside an environment, its supply of gas, its history of mergers, its spin, its growth, and even its eventual fading can be influenced by its place in the larger network. A galaxy near a dense node may experience frequent interactions, gas stripping, and rapid transformation. A galaxy along a quieter filament may continue receiving cold gas over long periods. A galaxy in a void may grow more slowly, with fewer close neighbors and a different rhythm of star formation. Environment becomes destiny. Not absolutely, but persistently. The same laws of physics operate everywhere, yet their outcomes depend on where matter happens to sit inside the web. This is one reason the universe cannot be understood by studying only individual galaxies. The full meaning of a galaxy includes the thread it belongs to, the node it approaches, the void it borders, and the dark matter halo that surrounds it. Even the Milky Way has such a context. It is not suspended in a blank arena. It belongs to the local group, which lies near larger structures and participates in broader flows of matter. On a still larger map, the local region is part of a filamentary environment within the web. The Sun, Earth, and all ordinary life are therefore situated not only in a galaxy, but on a cosmic strand. One thin part of a network whose full extent exceeds direct human imagination. This does not make Earth central. It makes Earth placed. It gives the planet an address inside an architecture of light and darkness. The strange consequence is that the universe becomes both more connected and more isolating at the same time. The web links galaxies through gravity and gas across enormous spans. Yet those spans remain so large that no ordinary communication or travel can cross them meaningfully. Matter can flow over cosmic time, but intelligence, if it appears in more than one place, may find the same structure almost impassable. Filaments connect the universe physically, while distance separates it practically. The web is a bridge for hydrogen, dark matter, and gravity, not a road for civilizations. This distinction will matter later, when the question of loneliness returns in a wider form. For now, the cosmic web shows that the universe has shape at the grandest level, accessible to observation. It is not a simple expansion filled with scattered lights. It is a vast arrangement of voids and strands, of nodes and flows, of bright galaxies tracing a mostly dark design. The filaments reveal where matter gathered after the early universe's slight unevenness was magnified by time. The voids reveal where matter thinned away. Together, they form the largest known structure, not held together as one solid object, but patterned by gravity across scales so immense that the word structure itself begins to soften. What makes the web most important is not only that it exists, it is that the visible parts are secondary. The shining galaxies, the star-forming knots, the clusters that dominate telescope images, all depend on a scaffold that cannot be seen directly in ordinary light. The web points beyond itself toward the darker inventory of the cosmos, toward the matter that gives it weight and the energy that slowly changes its future. To understand the web as architecture is only the next step. The harder step is to ask what the architecture is made from, and why most of that answer remains invisible. The visible universe is the part that learned to shine. Stars burn because ordinary atoms can collapse, heat, fuse, and release light. Gas clouds glow when radiation stirs them. Dust reflects and absorbs. Planets shine faintly with borrowed sunlight or internal heat. Every familiar image of space depends on this luminous minority, the small portion of matter that interacts with light strongly enough to announce itself. Yet the cosmic web already suggests that brightness is not the same as importance. The filaments are traced by galaxies, but the weight of the structure lies mostly elsewhere, in a dark component that does not emit, absorb, or reflect light in any ordinary way. Its existence is inferred from motion, from gravity, from the bending of background images, from the survival of galaxy clusters, and from the pattern of the early universe itself. This dark matter is not darkness in the poetic sense. It is not simply dust-blocking starlight, nor ordinary cold gas that telescopes have failed to notice. It behaves like matter because it gravitates. It gathers, clumps, and shapes the motion of visible things, but it does not behave like normal atoms. It remains outside the direct reach of light, present in the equations and maps, absent from the eye. The first strong clues came from systems that moved too quickly for their visible mass. In galaxy clusters, galaxies orbit under the pull of the whole cluster's gravity. If the only mass present were the stars and gas that telescopes could see, some of those galaxies should have escaped. Their speeds implied more mass than the light revealed. Later, spiral galaxies sharpened the problem. In a simple expectation based on visible matter, stars, far from the galactic center, should orbit more slowly than stars closer in, much as distant planets move more slowly around the sun. Instead, many galaxies showed outer stars moving unexpectedly fast. The rotation curves stayed nearly flat. Something massive surrounded the visible disks, extending beyond the bright spiral arms into large invisible halos. The stars were not disobeying gravity. The maps of matter were incomplete. Gravity was responding to mass that ordinary telescopes could not see. Over time, the evidence multiplied until dark matter became not a decorative correction, but a foundation of modern cosmology. Gravitational lensing shows the same hidden mass from another angle. When light from distant galaxies passes near a massive foreground object, its path bends. The foreground mass acts like a lens, stretching, magnifying, or distorting the background light. By measuring those distortions, astronomers can map mass whether or not it shines. Again and again, the lensing mass exceeds the luminous mass. In some colliding galaxy clusters, the hot, ordinary gas appears separated from the main gravitational mass, suggesting that most of the mass passed through with little interaction while normal gas slowed and heated in the collision. Such systems are especially important because they show dark matter not merely as a mathematical preference, but as a component whose behavior can differ from ordinary matter in a physical event. It is unseen, yet it leaves fingerprints in the shape of light itself. The cosmic microwave background adds an even older clue. Its tiny temperature variations preserve information from the young universe, when matter and radiation were still closely linked. The pattern of those variations only makes sense if dark matter was already present, providing gravitational wells into which ordinary matter later fell. Without it, the universe would have struggled to build galaxies as quickly and as abundantly as it did. Simulations that include dark matter form a cosmic web resembling the observed one. Simulations without it fail to produce the same structure. Dark matter therefore stands behind the architecture already traced by galaxies and voids. It is the invisible scaffold on which the luminous universe grew. The unsettling fact is that dark matter has not been directly identified as a particle. Experiments have searched deep underground, protected from ordinary background noise by thick rock. Particle accelerators have looked for signs of missing energy that could hint at new particles, leaving the detector unseen. Telescopes have searched for possible radiation from dark matter interactions in space. The leading candidates have changed, narrowed, or lost favor as results failed to appear. Weakly interacting, massive particles, once one of the most prominent possibilities, have not shown themselves in the expected ways. Other ideas remain alive: lighter particles, sterilely neutrinos, axion, modifications to early universe physics, or forms of dark matter that interact in subtle ways beyond gravity. The known effects are strong. The identity remains open. Dark matter is mapped more confidently than it is understood. Dark energy is even stranger because it is not primarily a hidden mass inside galaxies or clusters. It is tied to the expansion of space itself. In the late 20th century, measurements of distant exploding stars showed that the universe's expansion was not slowing as expected. Gravity should have been pulling matter together, gradually reducing the expansion rate after the Big Bang. Instead, distant supernovae revealed that the expansion has been accelerating. Something was causing space to stretch faster with time. The name dark energy was given to this unknown driver, not because it explained the mechanism, but because it marked the ignorance clearly. Whatever dark energy is, it dominates the total energy budget of the cosmos. Ordinary atoms make up only a small fraction. Dark matter makes up a larger share. Dark energy appears to make up the largest share of all. This means that the visible universe, the part of reality that stars and galaxies display, is not merely incomplete. It is a minor surface expression of a much larger unseen inventory. The best current cosmic accounting assigns only about 5% of the universe to ordinary matter, about 27% to dark matter, and about 68% to dark energy. These numbers are not casual guesses. They arise from multiple lines of measurement, including the cosmic microwave background, large-scale structure, supernova distances, and galaxy clustering. But the precision of the percentages can conceal the depth of the mystery. The largest components in the model are the least familiar: the atoms that build oceans, mountains, sails, atmospheres, and stars are the rare part. The universe that can be touched, seen, and chemically understood is not the main substance of cosmic reality. Dark energy changes not only what the universe is made of, but what it can become. Because space expands, distant galaxies recede from one another. Because the expansion accelerates, some regions are carried away so quickly that light emitted from them now will never arrive here. This is not motion through space faster than light in the ordinary forbidden sense. It is the stretching of space between regions. The farther away a galaxy is, the more expanding space lies between it and any observer in the Milky Way. At sufficient distances, that expansion outpaces any signal's ability to close the gap. Dark energy, therefore, makes the universe more isolated with time. It does not tear apart galaxies that are already bound tightly by gravity, at least under the standard picture. The Milky Way, Andromeda, and the local group remain held together. Galaxy clusters already bound may persist, but structures separated by wider cosmic distances drift toward permanent disconnection. The web remains visible now, but the far future favors solitude over immense timescales. Galaxies beyond the local gravitational neighborhood will fade beyond horizons. Their light stretch thinner and colder until it no longer carries usable evidence. A civilization born in that distant era might see only its merged local galaxy and a dark emptiness beyond. It could build a cosmology that misses the wider universe, not through failure of intelligence, but through loss of evidence. The expansion would have hidden the history that is still visible now. Dark matter and dark energy therefore pull the mind in opposite directions. Dark matter gathers. It helps structure form, deepens gravitational wells, draws gas into filaments, allows galaxies to grow, and gives the universe its skeleton. Dark energy separates. It accelerates expansion, enlarges distances, and gradually removes remote regions from contact. One component builds the cosmic architecture. The other changes the long-term meaning of that architecture by stretching its parts away from one another. Between them lies the ordinary, luminous universe, brief and bright, tracing a pattern it did not create alone and cannot preserve forever. This is why the scale of the universe is not only a matter of distance, it is also a matter of composition and fate. A map that shows only galaxies is a map of where the lights are, not a complete map of what governs them. The real universe includes invisible halos around galaxies, dark filaments between clusters, unseen mass-shaping motion, and a smooth, accelerating influence written into space itself. The more the structure is measured, the more visible matter becomes a guide rather than the full story. The galaxies mark the web, but dark matter carries much of its weight. The distances define the horizon, but dark energy decides how that horizon changes. The universe is not merely larger than it appears. It is made mostly of things that appearance cannot show. Once that is understood, the motion of galaxies takes on a deeper meaning. They are not only rotating inside their own halos or gathering along filaments. Entire regions are flowing under gravitational influences spread across hundreds of millions of light years. The Milky Way itself is moving with others toward a hidden concentration of mass, a large-scale pull embedded in the same dark architecture that has been shaping the cosmos from the beginning. The Milky Way is moving through the universe with a speed that feels almost impossible to reconcile with the stillness of the night sky. The stars appear fixed because their motions are slow against a human lifetime, and because Earth moves with them inside the same galactic system, yet the galaxy itself is not at rest. It rotates. It travels with the local group. It participates in wider flows shaped by the gravity of clusters, superclusters, dark matter, and the uneven distribution of mass across hundreds of millions of light years. One of the most revealing of these motions points toward a region of the sky in the direction of Centaurus, where galaxies in the local universe seem to drift together as if drawn by an unseen tide. The speed is about 600 kilometers per second, more than 2 million kilometers per hour. Not a gentle drift, but a vast collective fall. The Milky Way, Andromeda, and many neighboring galaxies are moving with it. The cause is not a single visible object, but a concentration of mass spread through deep space, partly hidden by the galaxy that contains the observer. Astronomers call this region the Great Attractor, a name that sounds more theatrical than the reality. But the underlying fact is plain. Something massive lies in that direction, and the motions of galaxies reveal its pull. The discovery emerged from measurements of peculiar velocity. The motion of galaxies after the general expansion of the universe is subtracted away. In a perfectly smooth universe, galaxies would recede from one another according to distance alone, carried by the expansion of space in a clean pattern. The real universe is not perfectly smooth. Dense regions tug on their surroundings. Clusters pull galaxies toward them. Voids allow matter to stream outward toward richer walls. A galaxy's observed motion is therefore a combination of cosmic expansion and local gravitational influence. When astronomers began mapping these deviations with increasing care, they found a broad flow. Galaxies across a large region were not merely expanding away from one another. They shared a movement toward the same part of the sky. The pattern was too large to be dismissed as chance. It implied a gravitational basin, a region where matter was descending toward a deeper concentration. The difficulty was that the suspected center lay close to the plane of the Milky Way, behind the dense band of stars, gas, and dust that forms the galaxy's disk. This is the zone of avoidance, a name that reflects observational frustration rather than empty space. The Milky Way blocks the view in visible light, hiding many background galaxies behind its own crowded foreground. The platform from which the universe is observed becomes a screen across the universe being observed. To see through it, Astronomers use wavelengths less affected by dust and surveys that can detect galaxies obscured in ordinary optical views. These methods gradually revealed clusters and superclusters behind the galactic plane, but the picture did not reduce to one simple object. The Norma cluster lies near the direction of the Great Attractor and is massive enough to matter. Yet it does not seem to account for the entire pull. Farther beyond it lies the Shapley concentration, an even larger gathering of galaxy clusters and one of the most massive known structures in the nearby universe. The flow toward the Great Attractor may therefore be part of a larger descent toward Shapley and surrounding mass. The name suggests a destination. But the truth is distributed. Gravity does not require a single center with a sharp edge. It responds to the total arrangement of matter, including matter that shines and matter that does not. The invisible component is essential here. Dark matter halos surround galaxies and clusters, adding mass that cannot be seen directly. A map of visible galaxies is only an approximation of the gravitational landscape. The Great Attractor is not simply a bright place hidden behind dust. It is a feature of a broader mass field, a depression in the cosmic terrain toward which nearby galaxies flow. The motion of the Milky Way is like the motion of water on a landscape too wide to see from the ground. A stream may appear to move toward a local valley, while the larger river system bends toward a deeper basin beyond the horizon. Laniakea gave this idea a more complete shape. By mapping galaxy flows, astronomers identified a supercluster-scale basin that includes the Milky Way, the Local Group, the Virgo region, and many other galaxies. Laniakea means immense heaven, and the name fits the scale without needing to exaggerate it. It is not a solid object with a clear physical border like a planet or star. It is a flow-defined region, a gravitational watershed. Galaxies inside it tend to move toward a common attractor region, while galaxies beyond other boundaries flow toward different basins. This way of mapping the universe is different from simply drawing around where galaxies appear dense. It asks how matter is moving, which valleys it is falling into, and which structures are linked by shared gravitational destiny. Under that interpretation, the Milky Way is not just located near the Virgo Supercluster or along a filament of the cosmic web. It belongs to a vast current. Its address includes motion, not only position. The galaxy is traveling inside a river of galaxies, and the river is shaped by dark matter, visible matter, voids, and the expanding background of space. But even this fall has a limit. Gravity pulls. Dark energy stretches. The Great Attractor draws galaxies inward, while the expansion of the universe works across larger scales to separate unbound regions. In the local universe, where structures are dense enough, gravity can still gather matter and resist expansion. The local group is bound. Galaxies and clusters are bound. Some flows toward nearby concentrations are real and measurable, yet on still larger scales. The accelerating expansion weakens the future meaning of these connections. A galaxy may be moving toward a mass concentration now and still never arrive in any simple sense. Space itself may expand enough that the relationship changes before the fall completes. The universe allows motion without guaranteeing reunion. It allows structure without making all structure permanent. This is one of the quiet paradoxes of cosmic scale. The Milky Way is racing through space, yet it remains trapped within distances so large that even rapid motion becomes slow. 600 kilometers per second is enormous beside any ordinary speed. But across hundreds of millions of light years, it becomes almost patient. A journey measured at such scales is not a voyage in the human sense. It is a gravitational trend unfolding over epochs. The galaxy does not experience the Great Attractor as a destination approaching on a calendar. It follows a curvature in the cosmic mass distribution, an inclination in the large-scale pattern. The motion is real, but its completion belongs to timescales on which galaxies merge. Stars exhaust fuel, and the larger universe changes its horizon. This gives the Great Attractor its importance. It shows that the universe is not only a set of nested structures, but a system of flows. The voids are not merely empty. They help push matter toward denser regions by offering less resistance in their interiors. Filaments are not merely bridges. They guide matter toward nodes. Superclusters are not merely labels. Some are basins where galaxies share a broad gravitational motion. The large-scale universe has a kind of geography, not of mountains and rivers, but of density gradients and gravitational watersheds. To live in such a universe is to be carried by motions far older and larger than the solar system. Earth orbits the Sun. The Sun orbits the Milky Way. The Milky Way moves within the local group. The local group flows within Laniakea. Each motion is real. Yet none can be felt directly from the surface of a planet because everything nearby shares the same fall. Stillness is local agreement. Motion is revealed only when the map becomes large enough. The Great Attractor also shows the limits of any simple center. For a long time, human thought placed Earth at the center, then the Sun, then perhaps the Milky Way by assumption. Modern cosmology removed each central claim, but it did not replace them with a universe devoid of direction. There are directions of motion, regions of influence, basins of attraction, and horizons of contact. None make Earth central. They make Earth situated. The Milky Way has a trajectory because mass is unevenly arranged around it. Its motion is one thread in the larger weaving of the cosmic web. The pull through darkness is not a sign of purpose, but of structure. Matter tells other matter how to move, and dark matter adds much of the instruction invisibly. The destination remains partly obscured, partly distributed, and partly overcome by expansion. That uncertainty is not a failure of the map. It is a sign that the map is becoming honest about scale. A galaxy is not an isolated island, and a supercluster is not a final container. The Great Attractor closes one illusion by showing that even the Milky Way is being carried. The next question is where that carried galaxy belongs when all the layers are assembled together. From Earth to the solar system. From the solar system to the galactic neighborhood. From the galactic neighborhood to Laniakea and beyond. Position alone is no longer enough. The full address must include the structures that hold, the voids that frame, and the motions that quietly carry everything forward. Earth's cosmic address begins with a surface that feels complete because it contains every ordinary direction a living creature can move ground underfoot. Sky above, horizon around the edges, and the turning of day into night. Yet that apparent completeness belongs only to the smallest layer. Earth is a rocky planet, a little less than 13,000 kilometers wide, wrapped in a thin atmosphere and moving around the Sun at an average distance of about 150 million kilometers. The scale is already large enough that sunlight takes more than 8 minutes to arrive. Yet, in the full address, this is still the innermost line, the street number before the city has even appeared. The Sun is a middle-aged star, neither especially massive nor especially faint. One ordinary furnace among hundreds of billions in the Milky Way. It holds the planets, dwarf planets, asteroids, comets, dust, and distant icy reservoirs in a gravitational system that stretches far beyond Neptune. But the Sun's kingdom is local. It is not the center of the galaxy, nor a privileged beacon in a rare place. It is one star moving with many others through the Orion Arm. a smaller spiral feature between larger arms, where gas clouds, young stars, old stars, and dust lanes trace a modest part of the galactic disk. Around that disk, the solar system is carried in a long orbit, taking hundreds of millions of years, so slow by human measures that the motion hides inside the apparent stillness of familiar constellations. The next layer is the local interstellar environment, a region of thin gas through which the sun is currently passing. This environment is not permanent. Stars move through clouds and cavities over time, and the sun's surroundings change as it travels. Around this local cloud lies the local bubble, a broad cavity of hot, low-density gas likely shaped by ancient supernova explosions. The solar system is therefore not merely inside a galaxy. It is inside a scarred and structured interstellar medium, a region where past stellar deaths helped clear a space through which the sun now moves. That detail gives the address texture. The place of Earth is not only defined by distance from a galactic center, but by a history of nearby stars forming, dying, heating gas, and opening cavities across the disk. The Milky Way itself forms the next great container, a barred spiral galaxy roughly 100,000 light-years across. Its disk is thin compared with its width, but its gravitational body is larger than the shining band suggests, because a dark matter halo extends far beyond the visible stars. At the center lies a supermassive black hole, surrounded by crowded stellar orbits, gas, dust, and the dense central bulge. Farther out are spiral arms and spurs where star formation continues unevenly. Earth's address inside the Milky Way is not central, not outermost, not exceptional in any obvious geometric sense. It is in a relatively quiet region where heavy elements from earlier generations of stars are available, where the sun has remained stable long enough for planetary history to unfold, and where the galaxy's larger hazards are distant enough to make a long biological story possible. That does not make the location chosen. It makes it conditional. Life, if it appears, must appear somewhere that allows time to accumulate. Beyond the Milky Way is the local group, the first truly galactic neighborhood. It contains the Milky Way, Andromeda, Triangulum, and many smaller galaxies, all bound together by mutual gravity and dark matter. The local group spans millions of light-years, yet it remains a small family compared with clusters beyond it. The Milky Way and Andromeda are the dominant spirals, approaching one another slowly enough that their future merger belongs to a far horizon of cosmic time. Around them, dwarf galaxies orbit, fall inward, lose gas, form stars, or become stretched into stellar streams. The local group is important because it is gravitationally bound. The expansion of the universe does not pull its members apart in the ordinary sense, because their shared gravity wins locally. In the far future, when more distant galaxies fade beyond reach, this bound family may be all that remains visible from this region. The address, then, is also a future boundary. What is local enough to remain gravitationally connected may one day become the whole observable sky for any later observer. The local group sits near the edge of the Virgo Supercluster, a far larger concentration of galaxy groups and clusters arranged around the massive Virgo Cluster. The Virgo Cluster itself contains well over 1,000 galaxies and dominates the region's gravitational landscape. Compared with it, the local group is a small outlying system, not part of the dense central city, but within the wider outskirts of its influence. Yet even the Virgo Supercluster is no longer the most complete description of the neighborhood. Galaxy flow maps show that the Milky Way belongs to Laniakea, a vast gravitational basin containing many thousands of galaxies moving within a shared large-scale pattern toward the Great Attractor region. Laniakea is not a solid object. Its boundary is more like a watershed line, drawn by the directions in which galaxies flow through the cosmic velocity field. On one side, motions descend toward one basin. On another, they fall elsewhere. This makes the cosmic address dynamic. Earth is not simply inside larger boxes. It is embedded within a hierarchy of motions, where each layer is defined partly by what it is bound to, partly by what it orbits, partly by what it flows toward, and partly by what expansion will eventually separate. Laniakea itself lies within still larger filamentary structure, part of the cosmic web. At this scale, the naming of individual neighborhoods becomes less like naming towns and more like tracing ridges across a landscape made of galaxies. Filaments link clusters and superclusters across hundreds of millions of light-years. Voids open around them. Walls and strands pass into one another. The Pisces-Cetus supercluster complex has been described as one of these immense arrangements, a filamentary region that includes the local supercluster environment in a still broader chain. Whether boundaries are drawn one way or another, the important fact remains that the Milky Way is not sitting in a uniform sea of galaxies. It is placed along a strand, near voids, within a flow, surrounded by a large-scale pattern made from dark matter, gas, galaxies, and emptiness. The address has become less like a postal label and more like a position in a living map of gravity. The final observable layer is the cosmic horizon, the sphere from which light has had time to reach this region since the early universe became transparent. This sphere is often called the observable universe, and its diameter is about 93 billion light-years in present distance. It contains an enormous number of galaxies, perhaps trillions, and an even greater number of stars. But it is not a container with Earth at the physical center. Every observer, wherever placed, has an observable sphere centered on their own location, because observation is limited by light travel time and cosmic expansion. Earth is central only to Earth's view. The same would be true for an observer in a distant galaxy, whose own horizon would overlap some regions visible from Earth and include others forever beyond Earth's sight. The full universe may continue beyond the observable horizon, perhaps far beyond it. The address therefore ends not with a wall, but with a limit of evidence. It reaches the farthest light that can arrive, then admits that the rest cannot be placed on the same map. This layered address changes the meaning of smallness. Earth is not simply small because its diameter is tiny compared with a galaxy, or because the Milky Way is tiny compared with the observable universe. It is small because every layer that once seemed final becomes local when the next layer appears. The planet is local to the solar system. The solar system is local to the Orion Arm. The Orion Arm is local to the Milky Way. The Milky Way is local to the local group. The local group is local to Laniakea. Laniakea is local to a filament of the cosmic web. The cosmic web itself is local to the observable horizon. And the observable horizon may be local to a greater universe that cannot be seen. Each enlargement does not erase the previous level. It preserves it as a smaller truth inside a larger one. That is why the address is humbling without being meaningless. Earth remains real. The Sun remains real. The Milky Way remains real. Their importance changes only because their context grows. In the end, the full address is not a sequence meant to reduce the planet to nothing. It is a way of understanding how much structure surrounds even the most ordinary point in space. A small rocky world carries oceans, air, minerals, living chemistry, and minds capable of reconstructing a hierarchy they can never physically cross. The next boundary is more severe than any layer already named. The observable universe is not merely another scale beyond the cosmic web. It is the edge of sight itself, a horizon made from time, expansion, and the finite speed of light, beyond which the map stops, not because reality ends, but because evidence can no longer arrive. The edge of sight is not a place where a spacecraft could arrive and find a wall. It is not a surface in space, not a shell of matter, not a final border marked by a last galaxy standing against nothing. It is a horizon made by time, light, and expansion. The universe has an age, light has a finite speed, and space has been stretching while that light has traveled. Those three facts together decide what can be seen. They also decide what cannot be seen. No matter how powerful a telescope becomes, the deepest images of the cosmos are therefore not pictures of an outer edge. They are pictures of an inner limit, the limit of evidence that has had enough time to reach this region of space. That distinction changes the meaning of the observable universe. The observable universe is not the whole universe with Earth placed at its center. It is the portion from which light and other signals have reached Earth since the beginning of cosmic transparency. An observer in another galaxy would have a different observable sphere, centered on that observer, overlapping this one in some places and reaching beyond it in others. Each horizon is personal to a location, not because the location is special, but because every observer is enclosed by the same rules of light travel and cosmic history. The common mistake is to think that if the universe is about 13.8 billion years old, then the farthest visible objects must be about 13.8 billion light-years away. That would be true only in a universe where space stayed still while light crossed it. Space has not stayed still. It has expanded the whole time. A very distant galaxy may have emitted light more than 13 billion years ago, when it was much closer than it is now. While that light traveled, the distance between that galaxy and the Milky Way grew. By the time the photons entered a telescope near Earth, the galaxy that released them had been carried far beyond the simple light travel distance. This is why the observable universe is roughly 93 billion light-years across in present distance, even though its age is much smaller when measured in years. The light has not outrun time. The stage itself has stretched beneath the light. At the deepest visible layer, ordinary galaxies give way to the cosmic microwave background, the oldest light that can be observed directly with electromagnetic instruments. It comes from a time when the universe was still young, hot, dense, and changing from an opaque plasma into a transparent cosmos. Before that transition, free electrons scattered photons again and again. Light could not travel freely through space because space was filled with charged particles that kept interrupting its path. The young universe was like a glowing fog, not dark, but unreadable. Then expansion cooled the plasma enough for electrons and nuclei to combine into neutral atoms. Once that happened, photons were released from constant scattering and began traveling through the universe. Over billions of years, expansion stretched those photons from visible and infrared light into microwaves. Today they arrive from every direction as a faint afterglow, carrying a map of tiny temperature variations imprinted when the universe first became transparent. Those variations are small, but their meaning is immense. They preserve the seeds of later structure, the slight density differences that gravity would amplify into galaxies, clusters, filaments, and voids. In the cosmic microwave background, the universe is not yet filled with stars and galaxies. It is a nearly uniform field marked by delicate irregularities, a record of the conditions from which all visible structure would later grow. To see it is to see the universe before the cosmic web had matured, before the Milky Way existed, before the sun had formed, before any planet could hold oceans or stone. it is not the beginning itself, but it is the earliest luminous surface available to sight. Beyond it, the universe is not absent. It is simply hidden behind the fact that light could not yet move freely. Other messengers may carry older information in principle. Neutrinos, nearly ghost-like particles, decoupled from matter earlier than light. Gravitational waves from the very early universe may also exist as a faint background, if the right processes occurred. But these signals are extraordinarily difficult to detect, and they do not change the essential boundary for ordinary astronomy. The cosmic microwave background remains the great visible curtain, the oldest light spread across the sky. Looking toward it is not looking outward to a distant shell in the usual sense. It is looking backward to an earlier state that surrounds every direction because every direction leads far enough back to the hot young universe. The edge of sight is therefore a time surface. Its distance depends on expansion. Its appearance depends on early physics. Its existence reminds cosmology that observation is always historical. Yet there is another horizon, quieter and more severe. The cosmic microwave background marks the oldest light that can be seen from the past. The cosmic event horizon concerns the future. Because the expansion of the universe is accelerating, there are regions so distant that light emitted from them now will never arrive here. This does not mean those galaxies are moving through space faster than light in the forbidden local sense. Rather, the space between here and there is expanding quickly enough that the photons cannot make headway across the growing distance. A beam of light can travel at the fastest possible speed and still lose the race if the road itself stretches faster than the beam can close it. This creates a boundary of causal contact. Beyond it, events can occur. Stars can form. Civilizations could rise. Galaxies can evolve. But no signal produced there now can ever reach the Milky Way. The separation is not practical difficulty. It is not a question of engineering or patience. It is built into the geometry of an accelerating universe. The event horizon gives cosmic scale a strange asymmetry. There are galaxies visible today whose current state is already unreachable in communication. The ancient light from them has arrived, so they belong to the observed past. But signals they emit now may never arrive, so they do not belong to a shared future. Knowledge can outlast contact. A telescope can receive a message from a galaxy as it was billions of years ago, while the galaxy as it exists now has slipped beyond any possible reply. The observable universe is therefore filled with ghosts, in a precise physical sense, images of places whose present can no longer be joined to this one by light. This is not because the universe is malicious or designed to frustrate observation. It is because time, expansion, and distance produce horizons naturally. Still, the consequence is profound. The cosmos is slowly removing parts of itself from reach, over very long timescales. Galaxies not gravitationally bound to the local group will drift beyond effective visibility. Their light will be stretched to longer and longer wavelengths, thinned and reddened until it becomes nearly impossible to detect. The cosmic microwave background will also cool and stretch, fading into a colder signal. Future observers, if any exist in the merged remnant of the Milky Way and Andromeda, may see a dark universe dominated by their local gravitational island. They may not have access to the evidence that now supports the Big Bang, the expansion of space, or the existence of distant galaxies in the same abundance. Their instruments could be better than present instruments and still inherit a poorer sky. The history of the universe is not guaranteed to remain observable forever. Evidence has an era. This makes the present cosmic moment unusually rich. The universe is old enough for stars, planets, heavy elements, galaxies, clusters, and intelligent observers to exist. It is also young enough, in the wider future of expansion, for the cosmic microwave background still to be measurable, and for distant galaxies still to fill deep images. The window is neither early nor eternal. It is temporary, a period when the universe has become complex enough to study itself and not yet so expanded that much of its story has vanished beyond horizons. The edge of sight, then, is not only a limit, it is a privilege defined by timing. The great cosmic map is visible now because light from the past still arrives, and because the accelerated isolation of the future has not yet erased the broader view. Beyond the observable horizon may lie more of the same universe, perhaps with galaxies and filaments continuing far beyond any possible signal. The laws seen here may extend smoothly outward, or the larger whole may contain features forever inaccessible to measurement. Cosmology can infer, constrain, and imagine, but it cannot receive data from regions whose light has not reached and never will. The keyhole remains a keyhole, even when its view is vast. Inside it lies the cosmic microwave background, the web, the voids, the galaxies, and the dark components whose effects shape everything seen. Beyond it lies not nothing, but silence from which no evidence has yet arrived. The next difficulty is that even within the keyhole, the earliest galaxies are not behaving exactly as expected. The horizon defines what can be seen. The newest telescopes are now showing that what can be seen may not fit the timeline that once seemed secure. The first galaxies do not appear in the record as gently as older models once expected. They emerge from the darkness with an uncomfortable brightness, not as fully explained objects, but as evidence that the young universe may have been more efficient, more crowded, and more chemically restless than the standard picture had allowed. The James Webb Space Telescope was built in part for this boundary, to look through infrared light toward galaxies whose visible and ultraviolet radiation had been stretched by the expansion of space into longer wavelengths. Earlier telescopes had already shown that the early universe was not empty for long. Webb sharpened that view. It found distant galaxies in greater numbers, with greater luminosity, and in some cases with more apparent maturity than many pre-launch forecasts suggested. The surprise is not that galaxies existed early. The surprise is how quickly some of them seem to have assembled enough stars, gas, dust, and heavy elements to become visible across almost the entire observable history of the cosmos. In the usual timeline, the universe begins hot and dense, then expands and cools. For a long period, there are no stars, no galaxies, and no heavy elements. Only dark matter, hydrogen, helium, traces of lithium, radiation, and the slow growth of density variations. Gravity begins gathering matter into wells. Gas falls inward. The first stars ignite, massive and short-lived, producing the first heavier elements in their cores and depths. Galaxies grow from smaller beginnings, merging, accreting gas, forming stars, and gradually building the structures that later become familiar spirals, ellipticals, and irregular systems. This story is not abandoned. It still gives the basic direction, but Webb has pressed on the timing. Some of the distant systems appear brighter than expected for their age. Some seem compact and intense, forming stars at rates that would be difficult to sustain for long. Some show signs of chemical enrichment earlier than simple models would prefer, meaning that at least some stars must already have lived, died, and seeded their surroundings before the observed light began its long journey. Heavy elements are clocks of a certain kind. Hydrogen and helium come mostly from the early universe itself, but elements such as carbon, oxygen, nitrogen, silicon, and iron are built through stars and stellar explosions. When they appear in a young galaxy's spectrum, they imply prior generations of stellar processing. The more enriched the gas appears, the harder the timeline becomes. It is not impossible for massive early stars to evolve quickly. Indeed, the first stars may have been enormous by modern standards, burning through their fuel in brief lives and returning enriched material to space with great force. But the puzzle lies in the combination of youth, brightness, abundance, and structure. A young galaxy can be bright if it forms stars furiously. It can be enriched if massive stars have already cycled material rapidly. It can be compact if gas falls efficiently into a small region. Each feature can be given a possible explanation. The tension grows when several features appear together, in more than one object, across a population larger than expected. The issue becomes less about a single unusual galaxy and more about whether the early universe as a whole was behaving differently from the assumptions built into the models. Spectroscopy is the crucial test because images alone can mislead. Arid, faint, distant-looking object may be a truly ancient galaxy whose light has been stretched by cosmic expansion, or it may be a closer object reddened by dust, age, or other effects. Webb's power lies not only in taking deep images, but in spreading light into spectra, where emission lines can reveal redshift, composition, ionization, and physical conditions. A confirmed high redshift galaxy is not just a smudge in a photograph. It is a measured object anchored by the fingerprints of atoms shifted across cosmic time. That does not remove every uncertainty, but it changes the level of the claim. A candidate is a possibility. A spectroscopic confirmation becomes a piece of the timeline. As more confirmations arrive, the early universe becomes harder to treat as a quiet prelude. It begins to look active almost as soon as it can be seen. This activity also matters for reionization, the era when the first luminous objects changed the state of intergalactic hydrogen. After the cosmic microwave background was released, neutral hydrogen filled much of space, absorbing certain ultraviolet light and making the universe difficult to see through at those wavelengths. The first stars and galaxies produced radiation energetic enough to ionize that hydrogen, gradually clearing the fog. The question is how quickly this happened, which sources did most of the work, and whether early galaxies were numerous and energetic enough to transform their surroundings. If Webb is seeing many bright galaxies at very high redshift, then those galaxies may have contributed more strongly to reionization than expected. Some may have carved ionized bubbles around themselves earlier than models predicted. A small galaxy, if dense and intensely star-forming, can become an outsized engine of radiation. In that sense, the early universe problem is not only about building galaxies, it is about changing the transparency of space itself. The deeper Webb looks, the more the first few 100 million years appear less like a slow dawn and more like a rapid ignition. Still, caution is essential. Distant galaxies are measured through faint signals, often near the limits of instrumentation. Their stellar masses, age, dust content, and star formation histories can depend on assumptions about how stars form and shine under conditions not seen nearby. A galaxy that appears massive may partly owe its brightness to unusual stellar populations or a hidden active black hole. An apparently mature structure may be less settled once higher resolution data or better models are applied. Some early claims have softened as measurements improved. This is normal science, not failure. The first view of a new regime is often dramatic because the uncertainties are broad. The task is to narrow them without losing the signal of genuine surprise. Webb has not overthrown the Big Bang. It has not erased the cosmic microwave background, the expansion of space, or the broad success of the standard cosmological framework. It has instead exposed places where galaxy formation physics may be incomplete. That distinction is important. A crisis in a model does not mean every layer beneath it has collapsed. It may mean that the recipe for turning dark matter halos, gas, radiation, feedback, turbulence, and stellar birth into visible galaxies needs to be revised. The standard model of cosmology gives the large scaffolding dark matter structure grows. Ordinary matter falls in. Dark energy later accelerates expansion. But within that scaffolding, the detailed physics of early star formation can still hold surprises. Gas cooling, magnetic fields, supernova feedback, black hole growth, dust formation, and the distribution of stellar masses all influence how bright early galaxies become. If early stars were more massive on average, their light output and chemical production would differ. If gas clouds collapsed more efficiently in dense young halos, galaxies could brighten earlier. If black holes formed quickly and accreted gas, they could add radiation that masquerades partly as stellar light. If dust behaves differently in primitive galaxies, inferred masses and ages may shift. Each possibility adjusts the picture, but none is free of consequences. A solution to one anomaly must not break agreement elsewhere. This is why the early galaxies are so valuable. They are not merely distant trophies. They are stress tests for cosmic history. They ask whether small-scale physics inside the first galaxies can fit inside the large-scale universe inferred from the microwave background and present structure. They ask how quickly darkness can become light, how rapidly simple gas can become enriched, how soon black holes can grow, and how efficiently matter can organize under the first deep gravitational wells. They also connect back to the broader question of scale. Seeing a galaxy from a time only a few 100 million years after the beginning means seeing across almost the entire observable past. The light is ancient, but the object was young when it emitted it. Its distance now is far greater than the age of its light might imply because expansion has stretched the intervening space. The galaxy is both a small, early structure and a marker near the horizon of sight. It sits at the meeting point of time, distance, and model uncertainty. The mind may want the earliest galaxies to be simple, because beginnings feel as though they should be simple. The data does not promise that. The young universe may have been physically simpler in composition, but dynamically fierce. Gas was denser. Mergers may have been frequent. Dark matter halos were assembling rapidly. Radiation fields were harsh. The first stars may have lived briefly and died violently. Under those conditions, complexity could arise quickly, not in the slow, graceful way familiar from mature galaxies, but in compact bursts of formation and disruption. The early universe may have been young without being gentle. That is the shift Webb has made difficult to ignore. It has turned the distant background from an expected sequence into a field of pressure. Each unexpectedly bright galaxy narrows the space where older assumptions can hide. Each confirmed spectrum becomes another point on a timeline that now looks more crowded near its beginning. The mystery is not whether the universe has a beginning in the hot, dense past. The mystery is how rapidly that beginning became structured enough to shine so strongly. The edge of sight has opened onto a young cosmos that appears already busy, already chemically active, already capable of forming luminous systems in numbers that strain simple expectation. This does not end cosmology. It makes the next question sharper. If galaxies grew too fast for comfort, and if the expansion rate itself refuses to agree between early and local measurements, then the problem may not belong to one corner of astronomy. It may be a wider tension in the way the universe's timeline has been read. The Hubble tension begins with a number that should have been a bridge. The Hubble constant describes how fast space is expanding today, measured by how quickly distant galaxies recede as distance increases. It is not a minor bookkeeping value. It reaches into the estimated age of the universe, the size of the observable horizon, the behavior of dark energy, and the consistency of the entire cosmic timeline. If the number is known, the story of expansion can be tied more securely from the hot early universe to the present day. If the number refuses to settle, then something in the chain of reasoning may be incomplete. The difficulty is that the universe seems to give two answers, depending on where the measurement begins. One answer comes from the early universe. The cosmic microwave background preserves a pattern of tiny variations from a time when the universe was only a few 100,000 years old. By measuring that pattern and interpreting it through the standard model of cosmology, researchers infer an expansion rate today of about 67 kilometers per second per megaparsec. A megaparsec is a large astronomical distance, a little more than 3 million light-years. In this measurement, every extra megaparsec of separation corresponds to roughly that much additional recession speed from the expansion of space. The other answer comes from the nearby universe. Astronomers build what is called the distance ladder, beginning with objects whose distances can be measured by geometry or well-calibrated stellar behavior, then stepping outward to more distant markers. Cepheid variable stars are especially important because their pulsation periods reveal their intrinsic brightness. Type 1, a supernovae. Bright stellar explosions with useful regularity. Extend the ladder farther into deep space. By comparing true brightness with apparent brightness, astronomers estimate distances to galaxies, then compare those distances with how fast the galaxies are receding. This local route gives a higher value, around 73 kilometers per second per megaparsec, sometimes a little higher or lower, depending on the analysis. The gap between these answers is not large to ordinary ears, but to precision cosmology it is severe. A difference of several units means the early universe and the late universe are not fitting cleanly into the same model. At first, the tension could be treated as a possible systematic error, a hidden flaw in one of the methods. That is the cautious instinct of science. Distance measurements are difficult. Dust can dim light. Crowding in distant galaxies can make stars harder to separate. Calibration steps can carry small biases from one rung of the ladder to the next. The cosmic microwave background also requires a model to translate ancient patterns into a present-day expansion rate. Perhaps the early universe inference was too dependent on assumptions. Perhaps the local measurements were being nudged by overlooked effects. For years, this was the most comfortable explanation. The universe did not need new physics if one of the rulers was slightly bent. But the tension has endured because each improvement has failed to make it vanish. Observations from space telescopes have checked the Cepheid stars with sharper infrared vision, reducing the effects of dust and crowding. Independent distance indicators, including the tip of the red giant branch and certain gravitational lensing systems, have offered additional routes across the same terrain. The local answer has not simply collapsed toward the early universe answer. Meanwhile, measurements of the cosmic microwave background have remained impressively consistent, and the standard model continues to explain a wide range of large-scale observations. The problem is, therefore, not that one side is obviously careless and the other obviously correct. The problem is that both sides have reasons to be trusted. That is what gives the tension its weight. A disagreement between weak measurements is inconvenience. A disagreement between strong measurements is information. The cosmic microwave background route is powerful because it begins with the oldest light. It reads the universe when matter and radiation were linked in a hot plasma, then uses the physics of that era to predict the expansion history that should lead to today. In the standard picture, ordinary matter, dark matter, radiation, dark energy, and the geometry of space evolve together in a precise way. Change one ingredient, and the pattern of the microwave background changes. The model has succeeded because it matches not only that ancient light, but also much of the later structure of the universe. Yet the same success makes the tension sharper. If the model is so good, why does it predict a slower present expansion than the local ladder seems to measure? The distance ladder route is powerful for a different reason. It does not begin with the infant universe and evolve forward through theory. It measures the nearby and intermediate universe more directly, step by step, using stars and explosions whose distances can be cross-checked. Its weakness is that each step must be calibrated carefully. Its strength is that it is anchored in the universe closer to the present moment. When it gives a faster expansion rate, it is not merely disagreeing with a number. It is saying that the universe today may be expanding more quickly than the early universe model expects. If that is true, the timeline itself has a hidden feature. Many possible explanations have been explored, and each carries a cost. One proposal is early dark energy, an additional energy component that briefly influenced the young universe before fading away. Such a component could alter the inferred scale of the early universe and bring the cosmic microwave background prediction closer to the local value. But it must do so without damaging the many other successes of the model. And that is difficult. Another possibility is that dark matter has properties not included in the simplest cold dark matter picture, perhaps interacting with itself, radiation, or another hidden sector in a subtle way. A third approach modifies dark energy, allowing it to evolve rather than behave as a simple, constant property of space. Others revisit neutrinos, gravity, cosmic curvature, or the possibility that local structure, including underdense regions near the Milky Way, biases nearby expansion measurements. None of these explanations has become decisive. Each can ease one part of the tension, but often introduces pressure somewhere else. Cosmology is tightly connected. A change made to fix the Hubble constant may shift galaxy clustering, the microwave background, supernova distances, or the age of the oldest stars. The universe does not allow one loose thread to be pulled without moving the fabric around it. This is why the Hubble tension is more than a dispute over measurement. It is a test of whether the standard model is complete enough to connect every epoch. The same model that relies on dark matter to build structure and dark energy to accelerate expansion may need another ingredient or a revised assumption. Yet the evidence does not demand a dramatic collapse of modern cosmology. It demands care. The Big Bang framework remains strongly supported. The microwave background is real. Expansion is real. Dark matter and dark energy remain deeply evidenced by their effects. The tension sits inside that framework, not outside it. Like a misaligned beam in an otherwise sturdy building. It does not prove the structure false. It shows where the load is gathering. The connection with early galaxies makes the pressure more interesting. Webb's unexpectedly bright distant galaxies and the Hubble tension are not necessarily caused by the same missing physics. They may belong to different parts of the cosmic story, one to the messy formation of stars and galaxies, the other to the expansion history of space, but both point toward the same general discomfort. The early universe, as observed more sharply, appears more demanding than the cleanest models expected. It forms luminous systems quickly, It leaves ancient light that predicts one expansion rate. It leads into a local universe that seems to expand at another. The result is not a single solved mystery, but a pattern of questions tightening around the timeline. Perhaps the solution will be modest, found in calibration, stellar populations, or the detailed behavior of cosmic dust. Perhaps it will be deeper, requiring a new field, a new particle, or a revised understanding of dark energy. The difference matters greatly, because a modest solution preserves the present architecture with small repairs, while a deeper solution would change how the universe's size, age, and fate are inferred. The Hubble constant is a doorway number. Behind it lies the full expansion history, and behind that lies the question of what space is doing. If the lower value is correct, the standard model remains closer to complete, and the local universe must be understood as biased or mismeasured in some subtle way. If the higher value is correct, the universe has expanded faster in recent cosmic time than the early model predicts, and the missing explanation may be written into physics not yet identified. If both are correct within their own domains, then the assumption that a single simple expansion history connects them may require refinement. The tension endures because none of these possibilities can be dismissed lightly. The universe has become precise enough to disagree with itself in public. That is an uncomfortable stage for any science, but also a fertile one. A vague universe can hide contradictions inside uncertainty. A well-measured universe cannot. The mismatch is visible because the measurements have become good enough to expose it. The next scale of the mystery lies beyond the numbers themselves. If the observable universe is only the region from which light has reached this cosmic address, then any error in the expansion history alters the interpretation of the horizon. The distance to ancient galaxies, and the size of the keyhole through which the cosmos is being viewed. The Hubble tension does not simply ask how fast space expands. It asks whether the map used to measure the largest possible distances is missing a rule, and if the map is incomplete within the observable universe, the unknown beyond that horizon becomes even more difficult to frame. Beyond the observable universe, the map does not end. It simply loses contact with evidence. The horizon around this region of space marks the farthest distance from which light has had time to arrive, not the boundary of all that exists. This is the quiet but severe distinction at the center of cosmic scale. The observable universe is a sphere of access, a bubble of information shaped by the age of the cosmos, the finite speed of light, and the expansion of space. Its edge is real as a limit of knowledge, but it is not known to be a physical edge. No measurement shows that galaxies stop there, or that space changes abruptly into something else. The most conservative assumption is that the universe continues beyond sight, with more galaxies, more voids, more filaments, more dark matter, and more regions whose light has not reached this address. The difficulty is that conservative does not mean small. Even a smooth continuation of ordinary cosmic structure beyond the horizon may be unimaginably vast, and some models of the early universe allow a hole much larger than the visible keyhole. The reason lies in inflation, a proposed period of extremely rapid expansion in the earliest fraction of cosmic history. Inflation was introduced to explain why the observable universe appears so uniform in temperature and geometry across regions that would otherwise seem too distant to have exchanged information. If space expanded enormously before the hot, dense state settled into the familiar Big Bang evolution, then regions now far apart could once have been close enough to share conditions. Inflation also helps explain why space appears nearly flat on large scales, like a tiny patch on the surface of a much larger sphere that looks flat only because the full curvature is far beyond view. The idea has strong motivations, though its detailed mechanism remains uncertain. What matters for scale is that inflation does not merely enlarge the universe. It may make the observable region a small remnant inside a far greater domain. The cosmic microwave background then becomes not the edge of a room, but the wallpaper visible through a narrow opening, smooth enough to imply that the wall continues far beyond the frame. Estimates of the total size depend on assumptions that cannot be checked directly, and responsible cosmology does not turn speculation into certainty. Some analyses suggest that, if inflation occurred in certain ways, the whole universe could be vastly larger than the observable part, perhaps by factors that break ordinary intuition. It may be only somewhat larger. It may be so much larger that the observable universe is less than a mote within it. It may even be infinite. Though infinity in cosmology is not a number waiting at the end of a ruler, it is a statement about geometry and extension, a claim that space does not close back on itself within any finite distance. The problem is that from inside one horizon, these possibilities can look nearly identical. A universe far larger than the observable one, and a truly infinite universe, can both appear locally smooth and flat. The keyhole cannot reveal the full room if the room is larger than any signal can cross. This is where the scale of the universe stops being only a question of imagination and becomes a question of epistemology. The study of what can be known. Science can extend inference beyond direct sight when there is a physical reason to do so. It can use the microwave background, galaxy clustering, gravity, and expansion to constrain possible shapes and histories. But it cannot freely inspect what lies outside the horizon. There are no telescopes for regions whose light has not arrived and never will. The unobservable universe is therefore not a fantasy region. It is a scientifically meaningful absence, a domain implied by the difference between what can exist and what can be observed. It may contain ordinary extensions of the same cosmic web. It may contain regions born from the same inflationary field, but settled into different conditions. Some speculative versions of inflation even allow a multiverse, where different regions possess different physical constants or vacuum states. Such ideas are not all equally testable, and the farther they reach beyond observable contact, the more carefully they must be held. Still, they reveal the strange consequence of the horizon. The largest possible structure may be permanently outside the evidence available to any single civilization. The universe could be much greater than its measurable part, and the measurable part could remain all that science can directly touch. This returns the question of loneliness in a changed form. When life is discussed on cosmic scales, the first thought is often biological. Are there planets with water? Are there atmospheres with the right chemistry? Are there stable stars? Protective magnetic fields? Long enough intervals? And the molecular pathways needed for living systems to begin? These questions matter. The galaxy likely contains many planets, and the observable universe contains far more worlds than the mind can meaningfully count. But biology is only one layer of the problem. Architecture may be another. Worlds are separated by distances that make travel hard. Stars are separated by years of light. Galaxies are separated by millions of years of light. Voids are separated by emptiness so broad that whole civilizations could rise and disappear without their signals crossing a significant fraction of the cosmic web. Even if life is common in a statistical sense, contact may remain rare because the universe is not arranged for conversation. Its structure allows matter to gather into stars and planets, but it also places those islands inside a widening ocean. Time deepens the separation. Two civilizations could exist in the same galaxy, but not at the same era. Their signals could pass before either has the means to listen. Their technologies could be brief, compared with the travel time of light across interstellar distances, across galaxies. The problem becomes harsher still. A message sent from one large galaxy to another may require millions of years. And by the time a reply could return, the original civilization may have changed beyond recognition or vanished entirely. Across the cosmic horizon, even light has no future path, no patience, no engineering, no devotion to exploration can overcome a causal boundary set by expansion. If intelligence exists beyond that boundary, it is not merely far away. It is disconnected from this region in principle. It belongs to reality. Perhaps, but not to possible exchange. The architecture of the universe, therefore, makes silence ambiguous. It can never be read simply as absence. Silence may mean that no one is there. It may also mean that someone is too far away, too early, too late, too faint, hidden behind dust, lost in noise, or beyond a horizon from which no signal can cross. The universe can be crowded and silent at the same time. It can contain many islands of awareness and still prevent them from becoming a community. This is not a bleak conclusion so much as a structural one. The same expansion that gives the universe its immense observable depth also limits future contact. The same cosmic web that links galaxies with gravity and gas leaves them separated by distances that no living timescale can easily bridge. The same dark energy that reveals itself through acceleration gradually removes remote regions from the possible future. The cosmos is not hostile. It is large, old, uneven, and expanding. Those facts are enough. From Earth, the keyhole remains astonishing. Within it are galaxies too numerous to hold in thought, voids wider than superclusters, filaments stretching through darkness, invisible matter shaping the luminous frame, and early galaxies challenging the sequence by which structure was expected to appear. The Hubble tension adds uncertainty to the expansion history. While Webb presses against the timing of the first light, dark matter gathers the scaffold. Dark energy widens the separations. The observable universe becomes not a finished answer, but a temporary opening, rich enough to reveal deep order and narrow enough to conceal the greater whole. That may be the most mind-bending scale of all, not that the universe is large, but that the part large enough to overwhelm thought may still be only the visible fraction of something beyond confirmation. The final image is therefore not a wall at the end of space. It is a lit aperture in a darkness that may continue without any reachable boundary. Earth sits inside that aperture, on a small world around an ordinary star, in a galaxy on a filament, within a horizon that is both immense and incomplete. The question is no longer whether the universe is big enough to humble the mind. It is whether the mind can accept that the known cosmos may be only the near side of a structure whose full scale is not merely unknown, but permanently unknowable. After the last horizon has been named, the universe does not become smaller or simpler. It becomes quieter. Earth remains where it has always been, turning in sunlight, carrying oceans and clouds, resting inside the gravity of one ordinary star. Around it, the solar system continues its long motion through the Milky Way. The galaxy continues along its wider flow through the local cosmic landscape, far beyond. Filaments stretch between clusters, voids open like dark chambers, and ancient light keeps arriving from a time when the first structures were only beginning to take shape. None of this needs to be hurried. The scale is too large for urgency, and the mystery is too old to depend on a single answer. What can be seen is already enough to change the meaning of distance. What cannot be seen gives the visible universe its edge of humility. The cosmos is not only a place of stars, but a place of horizons, hidden matter, accelerating space, and patterns that took billions of years to become readable. Some questions remain open because the evidence is faint. Others remain open because the necessary light has not arrived. Some may remain open because no light ever can. Still, within the keyhole, the universe has offered a remarkable view: galaxies forming early, dark matter shaping structure, dark energy widening the future, and a small planet capable of measuring shadows far beyond its reach. The scale does not erase meaning. It places meaning inside a larger silence. The mind can rest there, not with every answer settled, but with the shape of the mystery made clearer, softer, and more spacious. The known universe remains vast enough for wonder, and the unknown beyond it remains patient, inaccessible, and calm.